Till now, our study in this course has mostly gone around lower pair mechanisms, that is, linkage mechanisms. In the rest of the lectures, we um, see some glimpses of higher pair mechanisms. So, first, CAM mechanisms. Now, CAM mechanisms are essentially higher pair mechanisms, that is, line contact or point contact, typically line contact, to impart specialized complex motion from simple uniform motion, in which the driver moves in a simple motion and the driven component moves through a very specialized kind of motion. So this is typically used to give some motion for the opening and closing of valves, and similar little special kind of motion for which will occur once in a cycle periodically, or multiple times in a cycle also is possible, but pre-planned, pre-programmed sequence. And during the rest of the cycle, it does not. Another linkage-based mechanism for doing a similar thing is the general, so which I suggest that you look up sometime, and that is very interesting. So here, CAM is the driver number, which is attached to the uniform motion source, typically connected with the crankshaft of the engine for the opening and closing of the engine valves. And this, for most of the time, goes through uniform motion, and its profile has encoded the intended complex motion of the driven vessel, which will actually manage to open and close the valves or give whatever specialized motion to whichever component. The follower is the driven vessel, which is pushed by a jutting out segment of the cam profile to move out, thereby opening, and similarly to come down when that segment of the cam profile turns away from the bulb. So this is the driven number, and it gets its specialized motion from the cam profile. Now, in cam mechanisms, variety appears because of three reasons: different kinds of followers, knife edge, flat face, roller, spherical, and different kinds of connections, radial translating, offset translating, oscillating. Now, I will show you one picture in the next slide, in the context of which that will show one of this and one of this, but I will explain how others would happen, how others would differ from the one that is shown in the picture. And it also, the mechanisms also differ according to the different cam profiles for the different required motions. Now, once in a while, we will come back to this slide to see these things. Okay. Now, let us go to the next slide. Now, this is a cam. Actually, all the cams that we will be studying in this course, they are plate cams or disc cams, in which the cross section is uniform. Okay. It's a little disc, not of circular shape, but specialized shape, defined according to its profile, and that we decide according to the particular kind of motion that we want for the follower. So a plate cam with offset translating roller follower here this is the follower, this is the cam, and this solid line shows you the actual cam body, and perpendicular to this slide, that is the direction of the cosmic procession. It will have some difference. Okay. Basically for strength purposes. Now the follower motion is in this direction along this line, which does not pass through the cam, and that is why this E is the offset, and that is why this is the offset follower. Offset translating follower. The follower translates. It could have been that follower is hinged somewhere so that it rocks in a rotating manner, like this, oscillates in a circular path. That also could be possible. Okay. So now, if this offset were not there, if this follower motion line were passing through this cam center, then you would have radial follower. In this case, it is offset follower. Both translate. And if it oscillates in a rotary style about a point, fixed at a point, the follower, then it would be oscillating follower. So in the first line, first column, all the three, okay, so here, the second column, radial of translating, offset translating, oscillating, that you have understood. Radial translating is if the line of motion of the follower passes through the cam center. It is offset translating follower if the direction of the translation, line of translation of the follower has an offset from the cam center, the one that is shown in the picture, and oscillating if it rotates, rocks from one orientation to another orientation. And now, the one that I have shown in the picture, this is a roller follower because there is a little roller at the end of the follower which actually makes the contact. Okay. It is also possible that at the end you do not attach a roller to the follower, but you make the follower itself as a knife edge. Okay. Sharpen like pencil. Okay. The pencil cross section, you sharpen it and make it a knife edge. So that is a knife edge follower, and this is a roller follower. You can also make a spherical end of the follower, then you would have a spherical follower, or you can make a flat face at the end, that would be a flat face follower. So these are the different kinds of followers that you can think of. So now some basic terms related to the cam. So this is the cam. Part of it is circular, and that is the part which is circular. When that part remains in contact with the follower or roller at the end of the follower, then the follower does not, because this is rotating continuously. So from here to here, so this is at the same position. So nothing happens. Only when this segment comes in contact, then only the follower moves because it is pushed out. And after that is over, when again the circular portion comes, then who will bring back the follower? So typically, the way is to have spring dashpot so that after the push, after the positive push has been removed, then the spring dashpot arrangement brings it back. So that is how it typically works. So now this circular portion, if you complete that circle, then that circle will be tangential to the cam profile internally for a large segment of the cam profile and for this circle. So this circle is known as the base circle. Makes sense. So this is the smallest circle around the cam center, that is whose center is at the cam center, internally tangential to the cam profile. there are other circles also. We will see. Now, the point which is used to describe the follower motion, the most significant point in the follower, which can be used to trace its motion, is called the trace point on follower to represent its motion. In this case, it is P. So the base circle is a CV here. Trace point is P, center of the roller. In the case of knife edge follower, that point contact would be the trace point. Now, relative to the cam, as the cam rotates, follower moves intermittently. So relative to the cam, if you try to get the different locations of this trace point, I mean, relative to the frame, the trace point goes up and down, up and down. I mean, goes up, stays, comes down, stays, goes up, stays, comes down, stays. Okay. But related to the cam, where does it go? So for that, you typically can draw a configuration sequence with the cam as a fixed. It's an inversion of the mechanism. If you consider the cam as fixed, the frame and the follower moving according to whatever the cam motion could be, the negative of that. Okay. So in the cam fixed inversion, whatever is the path that the trace point traces is the pitch curve. Yes. So that would be typically, if you draw little circles at with their centers on the cam profile, okay, with radius equal to the roller radius, then the curve tangential to all those equal circles, all those dummy rollers, the where the center goes, so those center locations. So like that, if you join by a smooth curve, so then so that curve is the pitch curve. So you can easily get the pitch curve if you have the cam profile. So whatever is the radius of the roller, you make a little circle here with the center here, then with the center here, with the center here, with the center here. You get lots and lots of little circles all over. Now the curve tangential to all of them. That is the pitch curve. The locus of trace point in cam fixed. Now, the way internally tangential to the cam profile we made the base circle. Similarly, if we try to make the other circle a little bigger, centered at the same point, which is internally tangential to this pitch curve, then you will get this circle. The radius is simply the radius of the base circle plus the radius of the loop. So this circle is the prime circle. Circle internally tangential to the pitch curve. Here I have shown it by C. Fine. Now, if you see the angle between the direction of the follower motion and the normal to the pitch curve. The pitch curve normal would be something like this, and the direction which will pass through the trace point, of course. And through the trace point, you have the line of motion of the follower like this. In between the angle that you get is the pressure angle, phi. You see pressure angle in the sense of the term. That is the direction. There is a direction according to which the pressure gets. So that is the pressure angle between the direction of follower motion and normal to the pitch curve. So that's phi. And that pressure angle will vary according to the position in the cycle. And the point where the trace point, location of the trace point, where the pressure angle is maximum, that point is called the pitch point. And through that, the circle with the center here would be called the pitch circle. concentric to the base of the prime circle. And offset, I have already told you that this is offset. This is the distance of the line of forward motion from the camera. In the case of radial forward, this offset is 0. Okay. So now this is so far as the description of the cam. Now the forward doesn't need any description, it's just a body which has to be pushed and left alone. Okay. But what are the different kinds of motion that you may want from the forward? So typically during a cycle, you will require it to rise and stay there. Dwell means stay. Rise, dwell, return, dwell. Now it is possible that in some cases, at the end of the rise, you want the return to start occurring immediately. In that case, this dwell may not be there. In that case, it would be rise, return, dwell in the cycle. This is also fine. Now, what kind of motion? That is y displacement with respect to the angular position of the land. So, what kind of motion? So, there are several things that you may like to want. One is uniform motion. That is during the angular interval theta ri. Theta ri is the interval during which you want the forward to rise. Similarly, theta re would be for which you want it to return, and theta d1 would be this way, theta d2 would be this way, and this theta d1 might be 0. So all together would make the full cycle. So you may say, okay, let it rise uniformly during this entire theta rise. So in that case, this would be the analytical expression, and this is the. However, this purely is typically not, I mean almost never used, because here if you plot the velocity, then before this starts, the velocity is 0, and after also it is 0, and suddenly you have the velocity from here to here, which is lift L divided by theta L. So that's finite. So there will be a large acceleration in the beginning and the end, which you typically don't want. Okay. So you say that for a little while, let it rise with uniform acceleration, then stay with constant velocity, and then come down with a little deceleration. So that is possible. So in that case, you modify it like this. So velocity plot would show it better. There is for a little accelerated zone along which the velocity rises, which is velocity plot. And then the velocity remains constant, y dot, and then velocity plot. So that would be from here to here, it is linear. Before that, it is a little parabolic, and at the end, again, a little parabolic. This is a typical motion that we execute when we want to go from somewhere to somewhere else. We initially accelerate a little, then move the major portion with constant speed, and then at the end of the time we use a little deceleration to stop. So this is typically referred to as uniform motion with parabolic belts. Uniform motion with two parabolic belts at the end. So there is now if we say that till halfway we accelerate it and then start decelerating, that is, if the parabolic bends expand from two ends and just meet smoothly at the center, leaving no space for the uniform motion, then it is uniformly accelerated motion or completely parabolic. That is, first half one parabola, second half another parabola, joining smoothly at the center. Now, it could be that the acceleration magnitude here is less and here is more, or the other way around, with this segment and this segment not being both half but unequal. That's also possible. Now, if the acceleration and deceleration are same, then out of this complete L, half of it, L by 2, you would cover in theta Ri by 2 interval of gap motion, during which the accelerated motion would be half alpha theta square. Alpha is the corresponding second derivative of y intercept theta. That will be for the half interval, and for the rest half interval, it is L minus half alpha theta square. That is this. And alpha you can find out by imposing either on this or on this, that y at theta I by 2 should be L by 2. So when you impose that, you get alpha equal to. Now, the expression in the graph would be symmetric when the acceleration and deceleration of both the parts are same. There are other possible motions also, and only simple harmonic motion. And for that, the expression is something like this. And here, running from 0 to theta rise. So just put the values and see what you get. So cosine of an angle changes. Of course, this is simple harmonic motion, that is obvious. The cosine of an angle changes from -1 to 1. In the beginning, with theta equal to 0, this is 1, and therefore it is 1 minus 1. So in the beginning, rise is 0. And then it goes on increasing continuously till theta equal to theta rise. So that is cos pi is minus 1. So 1 minus minus 1, that is 2. That is why here you have L by 2. So the lift, total lift is here. So at the end, at theta equal to theta Ri, the rise y is equal to L. And you have a similar relation. There is a cute graphical method to produce this kind of theta versus y plot, which actually is important when you try to design and draw the CAM profile, which we will do later. Now, for that, what you do, you in the graph paper, you make theta I and divide it in a few segments, equal segments, and then at this side of the rectangle with length L, you make a semicircle. So the radius of the semicircle is okay. And then in whatever number of equal segments you divided this interval from 0 to theta I, in that many segments you divide this semicircle. Here 1, 2, 3, 4, 5, 6. So 30 degrees, 60 degrees, 90 degrees, 120, 150, 150. Now, from these points, you draw the horizontal lines to get its projection on this vertical line. Okay. So this position is here, this position will be here, this position is midway, and so on. So there are 6 projections. Actually, it is not 1, 2, 3, 4, 5, 6, but rather from this lower end is 1, 2, 3, 4, 5, 6, and here is 1, 2, 3, 4, 5. So now from here you project it and go and cut the one line, one vertical one line. From the second cut here, draw another horizontal line and go up to the second line. From the third, fourth, fifth, and 6 is, and then you connect these points to a smooth curve, and that is the graph of rise versus gamma. Rise of the follower versus angular position of the gamma. Now, if with 6 segments you feel that it is not precise enough, then you are at liberty to divide this into 12 segments, 20 segments, and similarly this also. Okay, and join 1 with 1, 2 with 2, 3 with 3, and so on, and then draw a smooth continuous curve. So that is the graphical way of using this motion graph of work, which is useful in designing and drawing the campus. Okay. And that drawing is very important because that drawing has to be sent for manufacturing. There is another. Okay, so this kind of a graphical method was there for the uniformly accelerated motion also. So here again, say for half of the interval, it has an accelerated motion. For the rest half, it has a decelerated motion. So you draw a line here of whatever length and connect the end line segment to whatever length. Connect the end of it to this position, the half of L, okay. And then divide this line segment into 9 equal parts or 16 equal parts, 25 equal parts, and then suppose it is 9 equal parts. So 9 comes here proportionally, 4 would come here, 1 would come here, which are parallel to this final line. And they will give you the ordinates y positions at the, if it is 9 pieces and these lines are at 9, 4, 1, then it would be for the half interval, it would be 3 parts, 1, 2, 3. So 1 vertical line and 1 inclined parallel to this line proportional, and that is this. 2 here, 2 square here. This is the square. So 2 square, 4 here. 3 here and 3 square, 9 here, and this square. So if you had divided into 16 parts, then this would also be divided into 4 parts, and then in this you would take the segments 1, 4, 9, 16, and make all these lines parallel to the 16. Okay. Similarly, this way. So you get graphical version. Very simple. Another kind of motion which is often asked for clamp follower, that is cycloidal motion. What is a cycloid? If you take a little circular disc and roll it on this straight edge like this, then the locus of a point on it makes a curve which is called a cycloid. So if the radius of this little circle is L by 2 pi, then by the time it completes one cycle, this point would again come here. Okay. And that would be there. So this circle rolling on the ordinate, rolling on the vertical line, this would give you the height of point P, which is y. And since it is rolling, so there is a translation and a rotation. So the translation part is just this, and the rotation part is this. So at theta equal to 0, you put theta equal to 0, this is 0. So see, the translation part is linear, so that is actually like this. And if you put theta equal to 0, then this is at 0. At theta equal to 0, this is also at 0. So it is at 0. P is here. And as you increase theta, this increases, this also increases, but this increases faster. So overall there is a positive difference. So it moves. P goes up, and its ordinate, its height gives you this also. At the end, theta equal to Ri. So if you put theta equal to Ri, so then this goes out. Sine 2 pi is again 0. But by that time, this is 2 pi by theta Ri. 2, no, sorry, theta Ri by theta Ri. Theta is theta Ri, right? So theta Ri by theta Ri. So here, when you put theta Ri, so you get this 0, and here you get 1. So the full motion will come out, which would come as with the uniform component also, the linear component also, because it's the in between this, by putting a subtractive component, makes this smooth. And the way to construct it graphically is to put a little circle of radius L by 2 pi here, and then this is the 0 position and 6 position also. 6 because we have decided, I have decided to show you 6 segments of this full interval. Whatever is the number of intervals that you want to divide it into the same number of intervals, this circle also has to be divided. So this horizontal position is 0 and n, the last one. In which case 0 and 6. In which case, whatever is the linear part giving, that's it. This part should be 0. And then, if it is in n part, if this abscissa is divided into n parts, then this circle has to be divided into n parts. So starting from 0, 2 pi by n, twice 2 pi by n, thrice 2 pi by n, and so on. Okay. So finally, it will be n times 2 pi by n, that is 2 pi, it will come to 0. So in this case, this is 6 segments, that is 1, 2, 3, 4, 5, 6, 60 degrees. And then for theta at this position, at the first segment, this is 0 of course. Okay. So 0th ordinate here, and from here, this bring it along the diagonal, that's it. Obviously, they're okay. At the first segment, this is the ordinate, and we have to cut from there. So this first segment, you project it on the vertical line first, and then from there, parallel to this diagonal, draw like this. Wherever you cut this ordinate one, that's the point. Similarly, second segment here, parallel to the diagonal, go like this, cut the second ordinate, 2. Third is here, so its projection is at the center, so come not parallel to the diagonal, but along the diagonal, come here. Similarly, for fourth, come here, for fifth, come here to the fifth ordinate, and then connect to it. You may not like that it could work with only 6 segments, so you happily make it 10 segments, 12 segments, 18 segments, 20 segments, whatever you like. And you get smoother and smoother profile of the function, rise function y. So these things we tuck into our head nicely, these background things, and in the next lecture we will see how we design the major broad dimensions and then the details of the camping. These things we will see in the coming.